Okay, so we remember that the derivative of e to the x is e to the x. Okay, but we know there's infinitely many exponential functions with different bases. So the question we're going to ask, what's the derivative of an exponential function of any base? So like b to the x. And how we're going to figure this out is we're going to derive this using the chain rule. Okay, so first of all, let's take b to the x, and we're going to get it in terms of e. Okay, so we're going to rewrite b like this. E natural log of b. Okay, that's like the composition of inverse functions. It's going to give us the identity. E to the natural log of b is just going to be b. Okay, so we had that. Let's do a little side bubble. E natural log, whoops, of x just gives us x. All right, so that's a property we had, and we went over at the beginning of the semester. Okay, so this is going to give us b, and now we're going to do b to the x. All right, and let's see, when we raise an exponent to an exponent, that's like multiplication. Okay, so natural log of b times x. So we want to find the derivative of b to the x. We want to find the derivative of b to the x. We don't have that formula. And we just determined that b to the x is equal to e to the natural log of b, which is a constant, times x. Okay, so we can figure this out using the chain rule, right? Because this is just a constant right here, natural log of b. So it'd be like e to the 2x. We know exactly how to find that derivative. It just looks a little bit funky because we have b instead of like the number 2. So what our chain rule says, by the chain rule, we take the derivative of the outside function first, right? E to the x, the derivative of that is e to the x. But the inside function stays the same. And then we take the derivative of the inside function. Well, let's see. Remember, natural log of b is like a constant. So what's the derivative? Here's a thought bubble. I should have done it in a different color. The derivative of a constant times x is just the constant. Right? In this case, c is the natural log of b. So times the derivative of the inside function, which is just the natural log of b. Okay. So let's explore this. E to the natural log of b times x. I'm just going to rewrite that maybe as a little side thought. E to the natural log of b times x. I'm going to move the x to the front because it's multiplication. And now we have a logarithm rule that if we multiply something by the logarithm, we can bring it into the argument as an exponent. All right, so now we have e to the natural log of b to the x. Again, that's that identity function. So this is saying what exponent gives e to be b to the x? So e to what power is b to the x? Well, e to that power is b to the x. It's the identity. So this whole expression becomes b to the x, and then we have the natural log of b, which is a constant. And that's our theorem. Let's write it and box it. So the derivative, this is one to memorize, of b to the x is equal to b to the x times the natural logarithm of b. All right, so we are memorizing that. Let's see it in action. Let's say we have a function equal to 2t cubed and we want to take the derivative of that function. Okay, so here we go. Let's write everything again in terms of u, because it's nice to be able to go back and forth. So let's call the outside function 2 to the u, and then that would mean our inside function, which is a function of t, you can even write that since it's a function of t, is t cubed. Let me write that u a little bit better. There we go. Okay, so we see we take our u function t cubed and we just plug it in for the u. And that's what we're going to be taking the derivative of. All right, well, according to the chain rule, this is equal to the derivative of f with respect to u times the derivative of u with respect to t. So the derivative of the outside function, 2 to the u, we just figured that out. That's 2 to the u times the natural log. What's the base now? It's not e, it's 2. Good, so it's our exponential function with base 2. All right, df du, and then what's the derivative of u with respect to t? 3t squared. How do I get rid of that? Oh, okay, so again, we have a u, but we started with a t, so let's not make it awkward. Let's give them t's, and u again is t cubed. Okay, and then let's clean it up a little bit. So again, this is all one big product. So let's see, we could do, let's do 2 times 3. We'll start with the 6. Oh wait, oh my goodness, what a horrible mistake. It's not 3 times 2, right? 2 is an exponential function. 2 is a base, 2t cubed. Glad I didn't write it fully. So this is protected. This is its own entity. We cannot multiply it by 3. All right, so let's see. Let's move 3t squared to the front. 3t squared, and then we'll multiply it by 2t cubed, and then we'll multiply it by the natural log of 2, and we'll call it a day. All right, I'm sure there's other way more complicated things we could do with that, but that's fine as it is. All right, so why don't you guys try one? So let me put up a problem, and then you guys can push pause. And you can try to do one with this exponential function on your own. So we're going to, again, find the derivative. If our r function is equal to 10 raised to the 2 root t power. All right, so go ahead and let's solve that on your own. Okay, so again, just for good practice, because why not? Let's write it in terms of inside function, outside function. So the outside function in terms of u is like 10 to the u, where u is 2 root t. Okay, and I'm going to change that square root sign to an exponent. Then I can actually take the derivative. All right, so according to our chain rule, if we wanted to find that derivative, we can look at dr du, derivative of the outside function, times du dt, derivative of the inside function. All right, and r is an exponential function. So according to our definition, the base b is 10. So it's going to be 10 to the u times the natural log of 10. All right, so that's the derivative of the outside function, times the derivative of the inside function. All right, we can just keep the constant out front. Bring that exponent down. and then subtract 1. 1/2 minus 1 is negative 1/2. Okay. And then, of course, we started with t's, so let's return to t's. So u is 2 root t. Natural log of 10. Let's see, 2 times 1/2 is 1. And t to the negative 1/2, I'm going to send that downstairs because it's a negative exponent. And t to the 1/2 is just the square root of t. So I'll write it like that. And that's your derivative. Okay, good. So what we're going to do now is we're going to revisit our trigonometric functions. And we were proving the trig functions using the quotient rule. But now let's prove some of these trig functions not using the quotient rule, but we can actually use our chain rule. So let's say we wanted to show that the derivative of the cosecant is equal to what? Have you guys memorized it yet? Negative cosecant cotangent. Okay, so we're going to do this using the chain rule. We've already done it using the quotient. Let's see another way of looking at the same thing. All right, and it kind of starts off the same. We would have to remember that the cosecant is the reciprocal of the sine. Okay, and at this point, this is where we use the quotient rule. The numerator function is 1 and the bottom function is sine. What we're going to do is we're going to think of the sine of x having an exponent of negative 1, because that would send sine of x to the bottom and, just be sine of x. And so if we think of it like this, now we can use our chain rule. Okay, so again, essentially what happens, remember 1 over x is like x to the negative 1. Okay, so that was that step right there. That's our thought bubble. Okay, so now we see that we have an outside function, raising something to the negative first power, and we have an inside function, taking the sine of something. All right, so if we wanted to find the derivative, we would have to use the chain rule. Take the derivative of our outside function first, bring down the exponent, and then subtract 1. Negative 1 minus 1 is negative 2. And the inside function stays the same. And then we take the derivative of the inside function. What's the derivative of sine? Have you guys memorized it? Cosine. Okay. So what do we have? We have the negative 1, so it's going to make this whole thing negative. Sine x to the negative 2. Negative is going to send sine of x downstairs to become sine squared x. And then cosine x is going to stay on top. Okay, and then let's see where we want to go. We want to go here. So we have 2 factors here. We only have 1 term here. So we're going to separate it. Okay, so separate up this sine squared x to sine times sine. And then we can split up our fraction. Sine times sine. Okay, so again, we wanted to get a cosecant, which is like 1 over sine. That takes care of that. And then we want a cotangent, which is cosine over sine. So that takes care of that. And then final step would just be to simplify. All right, so we can approach that little mini proof in 2 different ways.